who's now tasked with running 30 databases on a single machine, life has gotten a whole lot worse. All of a sudden, consolidation has made their job a lot harder. Every database you add to a machine makes that machine a little bit harder to manage, to back up, to tune. One database decides to run a query that consumes all of the I/O resources. The other 29 databases are negatively impacted, but there's really nothing they can do about it. It's sort of hard to manage the resources in an environment like this. Then there was the last alternative, the thing we call schema consolidation. In this environment, you have one server, so the system administrator is happy, but you also have one or very few databases. And instead of every application having its own database, which we had in this environment and that environment, we tried to take multiple applications and move them into a single database. So each of these schemas represents a different set of applications. This is actually something I've been asking people to do since the beginning of time. And it's easy to do if you start building your application that way. It's very hard to do if you've already built your application and you try to consolidate it with somebody else's application. When you try to go for the schema consolidation, you have various conflicts that will happen when you merge these applications together. If I have an application and I decide that my main application username should be application, and somebody else has an application and decided their main schema name should be that, we would not be able to consolidate those two. You can't have two of the same users in there. There's also political issues involved in this. If I put my application into this database in this schema, and I've got a set of DBAs who have been managing it, and somebody else has their schema over here with their data, they might not want their DBAs to be able to see my data. They might not want my DBAs to be able to see their data, and so on. So we're mixing our bits and bytes together. There's security-related issues. I don't want this person to be able to see this information, yet this person needs to be able to back up the database. If they can back up the database, they can, almost by definition, see this information. So there were security-related issues. There were namespace-related issues. There were issues with regards to even init.aura initialization parameters set inside the database. So the schema consolidation, even though it was the best approach, was not really practical. It was not feasible in the end because of these issues, the namespace collisions, the security-related issues, and so on. So these three different approaches to consolidating onto a single hardware platform were really challenging. In version 12, we came out with an architectural change to the database that actually allows us to get all of the good things about schema consolidation, yet maintain all of the properties of having separate databases. So if there was just one database, the DBA has one database to upgrade, to patch, to install, to configure, to back up, and so on. So that's one of the positive things of the schema consolidation. But when I had 30 separate databases, I had very strict security. I could have a DBA in one database who's not a DBA in the other database. I had no namespace collisions. I could have a user Scott in this database and a user Scott in that database, and so on. So what we've done in version 12 is change the database architecture in Oracle so that we can actually have multiple databases running inside of one single instance. We call this a multi-tenant database architecture. You know, if I ran separate database instances for each of these 30 databases, or I did that on this single host architecture, how many processes do you think you'd see in the operating system? If you start up 30 Oracle instances, you're going to see at least 600 operating system processes, if not 1,000. You know, because each database instance had its PMON, its SMON, DB writers, and so on. There's at least 20 processes associated with Oracle. And if I have 30 separate databases, okay, and I have those 600 processes for them, and then my application servers started firing up connection pools to the database, how many more processes would I see? Well, if each of those 30 databases just had a connection pool of 30 established to it, I'd see upwards of 900 more processes. So just by starting 30 databases on a single machine, I probably have well over 1,000, if not 2,000 or 3,000 processes running, and I haven't even logged into the database yet. I'm not running queries or anything. It takes a lot of resources to fire up 30 instances of the database. So one of the reasons for this new architecture was to allow us to start up one Oracle database instance. So all of a sudden, I have just 30 processes running instead of 600 to 1,000. And I can connect up to 255 individual databases to it without having to start up another set of processes. So I could run up to over 200 databases on a single machine using 30 processes as opposed to hundreds or thousands of processes. So the amount of memory we need, significantly reduced. The amount of CPU that the databases are using, even when they're not doing anything, is significantly reduced. Furthermore, when I start establishing connection pools to this database, I can use a database resident connection pool. Instead of every app server that wants 30 connections to my database, starting 30 processes on my server, I can share a pool of servers. So those connection pools established by the application server would connect to a thing we call a root container database. That root container database would allow them access to any of these databases that they were allowed to, that they were authorized to access. So instead of having thousands of dedicated servers for my connection pools, I have tens or hundreds. So I go from having thousands of processes on this machine down to having 100 or fewer processes able to do the same thing. All of a sudden, the amount of memory significantly reduced. The amount of management that a DBA has to do significantly reduced. In this multi-tenant environment, the Oracle Data Dictionary exists once, not once per database. When I go to upgrade, I have one thing to upgrade. If I want to, I can upgrade all 30 databases simultaneously. I don't have to patch 30 separate databases. I patch one database, and they're all patched. I set up a backup policy. It backs up the entire database. Each of these individual pluggable databases could have their own backup policies if they wanted to do backups more frequently or of a different kind. But at the simplest level, the DBA is managing just one database, even though there might be 30 or 40 underneath it. And this allows us to add databases and remove databases, something we typically don't want to do in an 11G or earlier environment, in a matter of minutes or seconds. Literally, to create a new database, if you went to a DBA in version 10 or 11, they would give you a very pained look on their face. They would not want to create yet another new database, because that's something else they have to manage, patch, secure, tune, monitor, and so on. But in this environment, creating a new database is something they can do rather instantly. They don't have to create another instance. They don't have to set up another backup policy. If they were using real application clusters, that new database is already configured for real application clusters. They manage and configure one instance with as many databases underneath it as they would like. So this new multi-tenant architecture allows us with no application changes. So if you're running in version 11 and you wanted to consolidate dozens of your applications into a single database instance, you don't have to change your applications. Your applications still connect to the database in the same way they did. They issue queries in exactly the same syntax. If I needed data from all three of these pluggable databases, your application would be using database links, just like they do today. From the application perspective, from a security perspective, nothing has changed. But from a manageability perspective, everything has changed. The DBA has fewer instances. Now, in this environment, I'm not saying you're going to take every single one of your databases and merge them into one instance, but you're going to merge them into fewer instances. Instead of having 30, you might have 3. Instead of having 300, you might have a few dozen. So the goal here is not to get to a single database instance, but the goal is to get to far fewer database instances. Because when you think about it, the database instance is what the DBA manages. By having fewer instances, the DBA has less to manage, meaning they'll be able to manage even more than they can today. Okay? The next thing to look at is in the area of engineered systems. You've probably all heard of a machine we call Exadata. We also have an Exalytics machine and a big data machine and so on. Those machines are relatively new. They came out in the middle of the last decade. But engineered systems are something we've actually been working on for a really long time. The first engineered system from Oracle came out last century in 1999. It was actually a Unix-based box. It was running the BSD distribution of Unix. It had Oracle version 8i installed on it, and it was a machine that you bought, plugged into the wall for electricity, plugged into the network for networking, and it was a database appliance. Its main claim to fame was the fact that everything was pre-installed and pre-configured. You bought the box, you plugged it in. It was sort of like a database appliance. And that's the concept with these engineered systems. When I'm talking to people about engineered systems, I usually start by asking them a couple of questions, like, in a data warehouse environment, how many DBAs in the world could tell you how many gigabytes of data per second they could retrieve from their disk into their database server? The answer is very close to 0. And the reason is most of us work in an environment where you have a database server, and that's managed by a system administration team and a DBA team. Then you have a network that connects that database server to a SAN, and that network is managed by the networking team. And then you have the SAN, and the SAN is managed by the storage administrators. And these are 3 and 4 different groups of people who don't necessarily like each other very much, right? Database performance problem, it's an I/O problem. You go to the storage administrators, it's working great. There's no problem over here. Must be the network then. Network administrators, everything's perfect. It's got to be the database. You go back to the system administrators, everything's patched correctly. We followed all the MLS notes. It must be your queries, right? And you just go around in this finger pointing all the time. When you need to be able to answer questions like this. If you have a terabyte database and you need to full scan a terabyte of information, the first question you should be able to answer is, how long is it going to take to get 1 terabyte from that disk drive into my database server? Because that's going to be the limiting factor on the performance of my queries, right? And in the SAN environment where you have the shared storage, somebody running a query on a completely different database server can be affecting your performance. You know, the same with OLTP. In an OLTP environment, in this architecture, what would happen if the log writes all of a sudden went from an average of 3 to 5 milliseconds to 7 or 10 milliseconds, which in computer terms is hardly measurable. I mean, it's less than the blink of an eye. But in computer terms, it's also an astronomical number. We've doubled the amount of time it takes for this response to come back. In a high-end OLTP system, something like this happening, just for 1 or 2 seconds, can completely hang a database. If all of a sudden LogWriter isn't responding as fast, people who've been running the transactions, their transactions are taking twice as long, but the transactions from the application server are arriving as fast as they always have. And all of a sudden, the number of users in my database doubles and then triples and then quadruples, and my database appears to be hung at that point in time. And this is all because we've got this shared infrastructure, the storage, the networking, the database server run by system administrators, and then the database sitting on top of this being run by database administrators. From my perspective, the biggest deal about an engineered system is it removes all of those groups. There's just one group, and that's the database administrators at that point. It's a very selfish approach to computing. I don't want to share my storage with you or anyone else. I don't want to share my network with you or anyone else. I don't want to share my operating system or my hardware with you or anyone else. This is a database in a box. It still has the SAN, but the SAN is inside the machine itself. It still has a network, but it's a private network. The only thing using it is the database. The DBA, for the first time, can answer the question, how many gigabytes per second can I get from my storage into my database server? And that's measured in 70 to 100 gigabytes per second. If you can get 70 to 100 gigabytes per second, all of a sudden you can scan that terabyte of information and then throw in other things like smart scans where we can offload portions of the where clause filtering down to the storage. You know, if I just go out and I buy a SAN and a network and a database server, every query I run that needs to access a terabyte of data needs to retrieve the terabyte from the disk and bring it up to the server. In this engineered system environment, instead of moving the data to the database, we can actually push part of the database down to the data itself. The where clause, we'll send that down with the IO read request, so that when we say give us these data blocks, we're actually saying give us these data blocks, but only the rows and columns that we really need. Here's our where clause. Filter this information for us. So all of a sudden, scanning a terabyte of data becomes something that we can do in under a second, utilizing compression, partitioning, the smart scan offload, and so on. The last thing I'd like to take a look at real quick is in the area of big data. There's a lot of things coming in the area of big data. Oracle Open World is happening next month. You'll be hearing about a lot of them. One of them that I'd like to be able to talk about right now is a new in-memory capability. The current production release of Oracle is version 12.1.0.2. It just came out about 2 weeks ago. And one of the new major capabilities inside of that version of the database is a new in-memory database format. On disk, we're going to store data exactly the way we've stored it in the past, in a row-oriented structure. This is perfect for OLTP, for queries that need to get small numbers of rows, because in an OLTP environment, you insert a row of data, you select a row of data, you update a row of data, you delete a row of data. Everything you do in OLTP is oriented around the row. Give me this row and all the columns. But then we get into analytic queries. And analytic queries might look at millions or billions of rows. So they're not looking at just a single row at a time or 10 rows at a time. And these analytic queries typically look at very few columns at a time. So there might be 100 columns in a table, but I want to see the sum of sales for the month of October. Right? I need exactly 2 columns for that out of the 100. In a row-oriented database, in order to get the sale date and the order amount, I'd have to read that block in, I'd have to find a row, I'd have to parse into that row to get to the order date column, and then parse over every other column to get to the order amount column. There's a lot of work just to get those 2 values out. With this in-memory format, we're storing data in a columnar format so that all the order dates will be stored right next to each other in sort of a vector format. All of the order amounts will be stored right next to each other in the same vector amount. So that when we need to find all of the sum of the orders in the month of October, instead of having to rip through terabytes of rows of information, we go and hit megabytes of columnar data that contains just the information we're interested in. Here's the order date, here's the order amount. Do the work you need to on this information that's already been physically co-located. And this is all happening in memory. This format of data only exists in the SGA. It is never persisted to disk. We use this information to derive the columnar information. As we make modifications to this data, we maintain these data structures, and then it's up to the optimizer to figure out which one it should query. So your application, when running against this new release of the database, will submit SQL just like it does today, and the optimizer will decide if it's going to use B-tree indexes and row-oriented information, or if, because the query is hitting a few columns but millions or billions of rows, it's going to scan through this in-memory format of the data. And of course, the DBA has control over which objects will actually be stored in memory in this columnar format, so they can pick what tables or partitions of tables, as well as which columns from those tables will be represented in this data store. This will allow you also to remove some of your B-tree indexes from your OLTP applications, because we have those indexes rather, on our OLTP tables in order to make some of our reports go a little bit faster. Those reports, instead of using indexes and row-oriented information, will now be redirected to use the in-memory format, and we'll be able to get rid of some of those indexes, thus speeding up our OLTP application. So it's sort of a win-win situation for everyone here. The analytic queries get this new in-memory format, no indexing required for it, and the OLTP system gets to remove some of those indexes. Those indexes are a major cause of performance issues in our OLTP system. Every time we insert a row, you have to update every index. Every time you delete a record, you have to update every index. Fewer indexes, better performance in general. So real quick, that was sort of an overview of where we've been with the database, where we're going in the future. Again, the current release is the second release of version 12 of the database. That's available for download on otn.oracle.com today, so you can start playing around with this stuff anytime you want it. We're going to take a quick break now, and then we're going to come back and hear some stuff about Application Express in here, and I'll be back a little bit later to talk about yet more new version 12 capabilities and features. Thank you very much for your time and attention.